afternoon and welcome to today's GCSE Science. It's a horrible wet day outside again. Today we're going to look at relative atomic mass and isotopes. We've sort of covered some of this when we're doing structure, but I think it's really important that you get to grips with the understanding of this. It's sort of more leaning towards higher tier stuff, but when you look at the specifications, they do expect people in foundation tier to know this as well, which it's quite complicated, really. So when you think about relative atomic mass, it's all based around carbon. Carbon was set as the thing that everything else was relative to in the 1960s, and that is set at 12. So carbon is considered to have a relative atomic mass of 12, which is why 12 grams of carbon equals a mole. Now, we've got to think back to our particles, and this is the old table. I'm forever referring back to this, but I still cannot get over how many times you do it, how many people get it wrong in exams. I think their brain's just empty somewhere. Okay, so we're going to think about this, and the main thing is we've got protons, and I've probably done that way too small. I can barely read it. Let me do that up a bit bigger in size. I don't know why I did it so small today. Right, so we go across there, charge and mass. Okay, bum, bum, bum. Proton, remembering all your particles in an atom, and the other one in the nucleus is the neutron. Okay, and the last one, which is whizzing around the outside, is the electron. Hopefully you can remember all those. So proton, if you remember, has a charge of +1 or 1+. It doesn't matter which way round you put it. If you're doing an exam, they'll understand. Okay, neutron has no charge, it's neutral, hence the name neutron, and the charge on electron is 1- or -1. If you just put a minus in, that's fine. Okay, but just remember that. The masses, now they don't expect you to remember at GCSE what the mass of an electron is. They don't really at A level anymore, but that's it. Okay, so it's very small. The other two have a mass of 1. They have relative masses of 1. Well, what relevance is that? So if we look at sodium, if you look on a periodic table, it will have 11 and 23. Okay, the smaller number is always the atomic number, and that always refers to the number of protons it has. Okay, the 23 is the mass number. Okay, and that one gives you the number of protons and the number of neutrons. So it equals, you've got 11 protons, and then you've got 23 minus 11 neutrons, which equals, by my maths, 12 neutrons. That's in a standard atom. Okay, this is where it gets a little bit more complicated, because sometimes, okay, we have things called isotopes. Now, carbon's the classic, but we're actually going to look at chlorine today. So chlorine, okay, all chlorines have an atomic number of 17. And then we get some that have got a relative atomic mass of 35. Oh, crikey. Why does that make it more complicated? Because there's another one naturally occurring, these naturally occur, of 37 and 17. The atomic number never changes, because that tells you the number of protons, and that tells you what type of atom it is, what element it is. Okay, so this number, if you look, it's got, how many protons has it got? Well, it's got 17. And how many neutrons has that one got? It's 17 from the 35, which is 18. Okay, and this one, protons is 17, and the number of neutrons is actually 20. And that's naturally occurring. So how do we work that out? Well, you've got, when they analyse naturally occurring chlorine, okay, this is what they find. They find you've got 75% of the 35, Cl35, I'll do it the other way around, Cl35, this is another way of writing it, and 25% of Cl37. So those are called the relative abundances. And that makes it a little bit difficult, okay? Because when we want to think about these and moles and stuff like that, we want them to be balanced. Now, I'm running out of talk again. So we have to work out what the relative atomic mass then, how many particles of things. We want to know the relative atomic mass of chlorine. Looking at that, the average atomic mass. Well, that's going to be quite difficult, isn't it? Well, sort of. What you do is we say we've got, so the relative atomic mass, can you see that? Yeah. Relative atomic mass equals the 35 times 75 divided by 100, because that's a percentage, plus 37 times by 25. This is your maths over 100. These are your percentages. So that equals 35 times 0.75, so 3/4 of that, plus 37 times 0.25, so 1/4 of that. Okay, and that comes out at, I've got it written down here because I can't remember the numbers and I'm not doing that maths in my head. That comes out at 26.25 plus 9.25, and lo and behold, the total comes out at, you add those together, we've got 0.5 and then it's 35.5. And if you look on a periodic table, a modern periodic table, instead of it saying 35, some of the older ones I have seen when I was growing up, we did have very, very ancient ones. But if you look at a periodic table now and you've got, look at chlorine, okay, you've got 17, you've got your 17 at the bottom, your atomic number. And at the top, if it's correct, and the ones you get given in exams is exactly the same, it actually says 35.5. Okay, and you'll notice that for several of the elements they have bits thrown in. All right, hydrogen, believe it or not, used to be the thing that everything was related back to. At the moment we're using carbon because carbon 12, but you get different proportions of hydrogen. And if you do the proper atomic mass, the relative atomic mass relative to what's in the UK, in the atmosphere and stuff, it actually comes out at 0.068. But you can see it's fairly close. So that one we just leave as 1. Okay, but you need to be aware of that when you are doing your science. Okay, that's why it's 35.5. It's because of relative abundance of the different forms of the isotopes, of the different isotopes. So an isotope is something with more neutrons or less neutrons. The other one that I like to think about is carbon. So we've got carbon, okay, carbon 12 is the common one. You also have carbon 13. That you don't tend to find in nature quite so much. That one is a heavy one. We tend to use it in research. And carbon 14 is the one that we use for radioactive. It's radioactive and it's what they use for carbon dating, because that one does occur naturally. And you can work out how much it decays, and that gives you how much the proportion of that to that tells you how long something's been dead, because you're taking that in all the time you're alive, and as soon as you die you stop taking it in. It's quite clever really, isn't it? But that one, the neutrons will be 6 That one, the neutrons will be 7, and that one, the neutrons will be 8. Okay, it's quite simple, really. Right, that's it for today. That's all the isotopes done. Tomorrow we're going to start looking at a bit of electricity, okay, and just reminding ourselves as to what it is and how it occurs. So please like, share, etc. And I will see you tomorrow. Any questions, obviously, drop me a line on joe@docnashsciencetutor.co.uk. I look forward to seeing you tomorrow. Thanks for watching. Bye now.